process output divided by process input, right? And process output is the PV, process input is the valve output. That time relates to, and this is that time. Here we are. That time, which is process delay, right? And it is usually associated with location caused by location of the transmitter, right? Because usually, like, we don't put a transmitter inside the furnace, we put it outside. So the furnace gets heated up, but the process fluid has to reach the transmitter, right? So location of the transmitter, which is why we also call this, another term for that time is transportation lag, because it needs to be transported to the transmitter. Okay? The last one, which caused a bit of issue, was time constant, right? You can forget about everything I said, that it is time taken to reach, what's that magic number? 63.2% of final value. Okay? So process gain, that time constant. Why do we need these three numbers? This defines process dynamics. Okay? The dynamics of the process, we want to put numbers on it. We can't just say, well, it's slow, well, it's fast. We want to give numbers to it. And to give numbers to it, I need to talk about the size of the change. I need to talk about how long it takes, right? So this is size of change, size of the delta. This is how long is the process taking, and this is just some delays that you have, right? So I want to tell you how long it's going to take. I want you to tell me the behavior of a person. You subject that person to some interesting stimulus, and how much he gets angry, how fast he gets angry, right? It's behavioral dynamics. Right? Okay, so then on the controller side, which is, okay, so this would have covered, but let me summarize everything here, so we'll be covering that as well. P is the proportional action. Right? I is integral. And D is derivative. To remember this is where the output is proportional to error. Here, integral output is proportional to error over a period of time. The output keeps on changing over a period of time. Derivative is output is proportional to the rate of change of error so ACD question. Very frankly, for those of you from 16.3, you'll never get asked this question. What is derivative? You won't get asked this question. Why? I don't think your assessors know the answer. There are maybe a few. One exception's your boss. Your PT. He's an exception. Chindara's very different, 16.3 principal, but he probably knows as much as my principal engineer in control. Very, very, very dangerous guy. I do not want to have any 16.3 get assessed by him because I pity those people. Because unfortunately you guys have 16.3, you have process control.
Yeah.
So Chindara can assess, he can assess my people. I would give him authorization to assess my people. So make sure next time you go for ACD, Chindara there, okay, never mind. Skip the assessment. He's scary. I have not met a principal engineer process who can talk controls as much as Chindara. But he's very passionate about controls. But hardcore process engineer, but very passionate about it. Okay, so we've covered all of this. We talked about gain. Oh yeah, we should mention, so let's say this is A. Let's talk about units. Right? We say proportional, integral, and derivative. So proportional units here is dimensionless. I fits in. And here's something maybe you guys need to be aware of. You have minutes for, so it's actually minutes per repeat. But in a DCS you'll see minutes. And this is for Fox in Honeywell. But if you go to Yokogawa, it's in seconds per repeat.
Yokogawa
right?
in second.
Yokogawa. Which is an issue. Where's the issue here? The issue is if you transition from a Yokogawa system to a Foxborough system. Why? So you want to put 2 minutes, okay, I will use 120 seconds. Then I go to a Foxborough system and I type 120. Right. Now, if you think about it, that's not an issue.
It's okay.
It's okay because 120 minutes of integral is extremely slow. What if you did 120, so you put 2 minutes in Foxborough, and now you go to Yokogawa and type 2
seconds.
It became 2 seconds. And your loop suddenly goes, jumps. So you have to be aware of the units when you're working on the DCS. Right? So it's either minutes per repeat or seconds per repeat, but in some, and we're not talking about DCS based, but standalone controllers. Standalone controllers. So this is usually in DCS. In standalone controllers, you'll get the other version, which is repeats per minute or repeats per second. Okay? But these are not common. be aware. So point to know, be aware of the units used in your DCS. Okay? In D, it is always minutes or seconds. So this is dimensionless, and you use controller gain, which sometimes we say K, or we use proportional band, right? Gain is only used in Honeywell, proportional band in Yoko and Fox.
Keep 100 over PP.
Right? Okay, so we have covered 100 slides already. We've covered 150 slides, so sorry, I should then talk about the overall, right? So the overall equation, which is the change in output is equal to K times error, K over interval time, error and that speed term, so we call it P term. This is the I term, and that's the D term. It's just terminology we use. P refers to the K over here, I is the interval time, D is the, when you say, oh well, the D term gets very big, it means the whole of this part gets very big. Right, so it's just a terminology we use. Alright, so we've done 100 slides, and control loop structure, I'm not going to cover it. Just to recognize that there are a lot of options, right, in the DCS.
With the P-only controller,
Yep.
Does it mean that it only applies one corrective action?
No. And there, it doesn't apply. So if you have, and it's a good question, it involves a bit more discussion, but the reason is that in the DCS, although I draw this equation, you find this equation in just about every textbook. This is not what's implemented in the DCS. What is implemented in a DCS is, if you think about it, if I implemented this equation in DCS, I calculate error now, and I implement it, right? But DCSs work on discrete basis, not on an analog base. That means in DCS we run the controls every second or every 2 seconds. So you go into a control block, and it's like a standard computer, we'll run it at a cycle. in like Foxborough, they call it BPC, block processing cycle. So it's how often you run the block. Now think about it. Let's say you have something running 50% is at point P. Error 0. Level controller, and the level drops. 50 drops to 40. Impossible, but let's just say it happens. 50 drops to 40. What do I get? Instantaneously, I get an error of 10%. Right? What does this block do? Let's say it's pure proportional, right? Gain of 1. Error 10%. This calculates an output change of 10%. But the block is running at 1 second intervals, right? So the block processes the 10%, it sends an output change of 10%, then it comes back again after 1 second. Okay, what's the error? 10%, oh my god, change the output by another 10%. What happens? In 5 seconds, you've already hit 0 or 100%, right? In this case. So the problem with discrete systems that process every second, if it continuously sees an error, it will change its output. Now the way the DCS vendors get out of this is by not using error. They use, so the actual equation inside all DCSs is changing output is equal to K multiplied delta error. Now what does delta error means? It's error T minus error T minus 1. That means it takes the last error, subtract it with the current error. So let's go through that same scenario one more time. Suddenly level drops. I get 50, 40, I calculate error 10%. Second time I process. I calculate error 10%, but the last error was 10%. So the delta error is 0. No change in it. Okay? Now, to answer your question, so strictly speaking, the first time I run it, I get 10%.